Thanks to the Talk Python team who sponsored this episode of the Engineered Mind podcast. If you want to learn Python and delve into exciting topics like data science, web development, or building apps, feel free to visit talkpython.fm/mind to find your next level and get a 10% discount. Also a big thank you to all my patrons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast. In this podcast we cover topics such as engineering, artificial intelligence, neuroscience and other interesting topics to educate, inspire and engineer people's minds all around the world. I'm your host Jozsef, and for this episode of the podcast I'm very happy to have Dr. Jozsef Nagy, CFD engineer at eulerian-solutions, on my show. Jozsef graduated from the Vienna University of Technology in physics and finished his Ph.D. in chemical engineering. For 6 years he held the position of a postdoc at the Johannes Kepler University, where he worked on polymer materials. He is the chair of the technical committee for tutorials and documentation in the OpenFOAM Governance System. At this point, he has the biggest YouTube channel with specialized tutorials for learning CFD with OpenFOAM. His areas of interest are diverse: multiphase flows, complex materials, porous media, fire and species dispersion, fluid-solid interaction, short FSI, and model development and implementation, as well as custom workflows for specific applications. In this podcast, we talked about the open source tool OpenFOAM, advantages of the tool, tips when getting started with OpenFOAM, Jozsef's company eulerian-solutions, and tips on how to assess your CFD results. For updates on upcoming podcasts, projects and videos, make sure to follow me on Twitter as well as on Instagram. To join my weekly newsletter engineeredmind.sh, where I share exclusive content, visit joseph.substack.com. And now, ladies and gentlemen, here's my podcast with Jozsef Nagy. Finally, we have the time to meet, at least digitally. Can you give us maybe like a 1-minute bio of who you are and what you do?
Yeah, sure. So thank you for having me. I'm glad that I can be here and talk to you. And so my name is Jozsef Nagy. You might know me from conferences or hopefully from papers, but most probably you know me from YouTube, from my YouTube activity where I share videos how you can start with OpenFOAM and then come to a point where you can start with your own projects in OpenFOAM.
That's so cool. Also, we want to put some emphasis on OpenFOAM today. Could you maybe first explain for an absolute beginner what is OpenFOAM and why do we use it?
Okay, so OpenFOAM is a CFD tool, so computational fluid dynamics tool to calculate numerically problems in fluid dynamics. And it is an open source tool, because some consider it to be a free tool, but I really like the description that it is without first initial financial commitment. So you can just download it, but although you don't have to pay anything up front, but you do have to spend time into it. So it is an open source tool, and the advantages is that you have the possibility to control a lot of settings, you control the mesh, control the boundary conditions, and you can also take a look at the source code. And if some models are not implemented, then you can implement those for yourself.
Got it. Where do you see the big advantages from OpenFOAM compared to other maybe commercial software tools?
The big advantage is, as I mentioned, that you have the control. It's not a black box system, so you can really trace down the error to the code or to your mesh or to your numeric settings. And another big advantage is that you can parallelize it. You can run it up on thousands of cores if you have the hardware. So you can really to do large simulations, and there are the license costs, because commercial codes can cost a lot. So especially if you're alone, if you're an engineer and you have your own company, or it's a small company and you cannot afford the license costs, the yearly license costs of a commercial code, then OpenFOAM is a good alternative for that.
Got it. You're also talking about company. You also have your own company called eulerian-solutions,
exactly,
right?
Yes.
Can you maybe explain for us what do you do there and what can you offer to people?
Sure. So I started my company approximately 2 years ago. Before I was at the university here in Linz at the Johannes Kepler University, and here in this company I focus on consulting in the field of OpenFOAM. So I'm not concentrating on an industrial direction, so for example automotive industry or chemical engineering industry, but I focus on OpenFOAM specific topics for all kinds of industries, and I offer them consultant projects where I solve problems for them, but I also help them set up a workflow for their problem. Because in OpenFOAM you have a lot of solvers, a lot of models, and often it is very difficult to come from the tutorial to your actual problem, and I help them set up a workflow from geometry creation over mesh setup, selecting between snappy hex mesh and CF mesh, and then the correct mesh setups, then the correct boundary conditions, the correct numerics for their problems. And of course, if the models are not enough, the out-of-the-box models that come with OpenFOAM, I also offer the implementation of new models and also training, and especially on-site training for the employees at the company, and focused on their problems. So it's not a general training. Of course, you have to start with something general, but I like to then narrow it down to their problem settings.
That's actually super good, because you do the tutorials, you have plenty of tutorials online, obviously, but then having your own problem is something completely different, right?
Exactly, yes.
Yeah. What would you say, what are the biggest bottlenecks when someone starts with OpenFOAM, or even an expert in OpenFOAM?
Okay, so the main problems that I see, especially with newcomers, is that they want to go in for the kill immediately. So they want to go through 3 or 5 tutorials, and then they want to go for the actual problem. And this is problematic because at each individual steps in your CFD setup, you can make a small mistakes which has a consequence at a certain point. For example, your simulation crashes with some floating point exception, and it is very difficult to then trace back the error to a problem in the geometry or a problem in mesh setup. So what I like to advise, and I focus on, for example, in several videos on Patreon, on that, how you can improve your CFD work and your career as CFD engineer, that you start small, start with a tutorial, then several tutorials, then try to set up a very, very simple case, which is more or less the same as your final case setup, but really simplified, just an inlet, an outlet, and a wall, and with the simplest numerics, simplest physics, and then increase the physics. So that, for example, the thermodynamic settings go from an ideal gas law to a more complex law, and then it's usually hand in hand with first and second order, and then do it on that small case with a very good quality mesh. And then once you have a good idea about the physics and then also the numerics, then you can go and then increase the complexity of your geometry to the level that you require. So that do this step by step, and I know that it takes longer, but believe me, if you have your problem, an error in your complex geometry, it takes a lot longer to trace it back to a problem than do it step by step.
Makes absolute sense.
Yes?
Yeah, you can continue if you want.
Okay, yeah, so maybe what's another problem is that maybe people consider OpenFOAM a free version of Fluent and a free version of CFX, and this is what we talked about earlier, that you have to go in with a different mindset. It's not a free commercial code, but it is an open source code where you want to have the possibility to control, but because you have the possibility to have a lot of control, but this also means that you have to be able to control several things. Maybe not everything, but several things. So you have to go into OpenFOAM with a different mindset. And I see that people consider OpenFOAM kind of like the WinRAR in the CFD world, that you just download it and then click, and then that's it. It should work. But that's not the correct mindset that you should use when you are going into and starting with OpenFOAM. You should be wanting to have the control and then nail down the things that you can fix for your problem settings, and then understand what you have to change.
So if someone has a problem with his specific geometry, for example, how can they reach out to you? Is it, for example, via Patreon? As you mentioned, I saw that you offer some help via Patreon.
Yes, on Patreon I have a tier where I offer my patrons that I support them with their CFD projects. So they can send me their problem settings or GitHub or just a Dropbox, and then I take a look at it. So I'm not solving the problem for them, but I'm helping them. And I think this is a more valuable thing, that they can find out what mistakes they made. So I'm just guiding them through like a supervisor in their CFD project. So this is one possibility. If it is just a small issue, then you can always post below YouTube video. I try to be up to date. I quote up to date, for example, on the YouTube comments. It can be sometimes take a lot of time to catch up on everything. But if it is a small thing, then I'm happy to answer it in the YouTube comments. Otherwise, the Patreon way is an alternative, yes.
Got it. For what a lot of people ask is especially boundary conditions or the numerical settings. Where do you see the biggest problems there? What do you think in your case, maybe when you started, what was the biggest issue for you? Was it more boundary conditions? But I think it's more intuitive, right? You have an inlet, you have an outlet, you have the walls. It's kind of physical, you understand it. But what about the numerics? What do you think there?
And both are very difficult, because I know there are boundary conditions, fixed value, zero gradient, and Nuti wall function, K, Q are wall functions, and then newcomers are confused by them. I mean, after a while, you get the combination of the pressure boundary condition and the velocity boundary condition, but still for newcomers, it's difficult to understand, especially turbulent inlet. That is what can be a bit difficult to grasp, but actually it is very simple. And for example, I am currently on a simulation project on Patreon where I really like to concentrate on the case setup and initial and boundary conditions. So it is really just test those, and I really try to describe that on YouTube and also on Patreon. What is behind the boundary conditions, and I think boundary conditions are nicely documented in OpenFOAM. So if you find out the path where you can find the boundary conditions in SRC and then finite volume, then you can. There is a big collection of boundary conditions, and if you open up the header file, there is usually a very good description what those boundary conditions do. Now the numerics, that is a bit more advanced, and I mean, for newcomers it really just boils down to first or second order discretization schemes, because everything else is a lot more complex. And so upwind or linear upwind or limited linear, and for that my advice would be just take a look at what I use in my videos or what the OpenFOAM tutorials use, and then try to use those rather than test them. First, upwind is always a good idea as a starting point, but of course upwind can still make a big error. Recently I had a project where the difference between first and second order was 17% in pressure drops. So you should take a look at discretization schemes, and so you might have heard of grid dependent study. So you refine the mesh, and then you see whether your results converge to a mesh independent result. The same can be done also for the numerical settings. So see what is the change in pressure drop or the outflow value, whatever you are interested in, and then change the numeric settings and see how whether they change. And also what is also very important, and the number of iterations, and not a lot of people talk about that. The autocorrector, then the end correctors and the non-orthogonal correctors in the pimple loop. So if you have the time, then it's just one setting, it's just one number or two numbers that you change, and then you make a parameter study, especially what I mentioned with a small case, where you already set up your physics, and you have a small case setup where you can run the simulation in 15 minutes. Then you can run 10 simulations with different numbers of autocorrectors, and then see do those the increase of iteration number change your results. So other than that, everything else is a more advanced stuff. So then you really have to go into the literature about the matrix solvers or the source code itself, and I think that a lot of people will have the time for that. So what people might have time for is this kind of grid-dependent study, so this numerical study where they on a simple geometry you can kind of test what is the limit, what is the best compromise between runtime and accuracy.
Where do you see the biggest problems? Let's say we walk through a project that you maybe help people with. Let's say the first step, of course, is always the pre-processing part, right? And then we have the processing part and the post-processing part. If we now have a look at the first part, pre-processing, where do you see the biggest mistakes happening?
That pre-processing is something tedious. It's just you have to deal with. But I really like the quote of Professor Jasak, that who owns the mesh, owns the simulation. So, and this is still true, because it is very simple to run Snappy Hex Mesh. It finishes in 10 minutes and then you have your mesh. But I remember back during my PhD, we worked with Fluent and with Gambit. I'm not sure whether you worked with Gambit. It is a very old pre-processing mesher for Fluent. And for a project back then, I spent 2 months just on the mesh, because it was otherwise impossible for the simulation to run. So, and I don't say that everybody should invest 2 months into meshing, but it shouldn't be just a tedious pre-processing step. So for Snappy Hex Mesh, the geometry is already crucial, because with your geometry, with your STL files, you already predefine your later boundaries. So you should really think about at the beginning, what are the boundaries that you want to control in your simulation, and then separate your STL file accordingly. And of course you can combine it into one STL file, but still, which are the boundaries that you want to control. Then the surface triangulation can be sometimes a problem of the STL file. So it is also a question whether your CAD tool does have a good surface triangulation while exporting a STL file. And then, so Snappy Hex Mesh can be very overwhelming, the settings. So I like, if you have the time, try Snappy and CF Mesh, because in some cases Snappy Hex Mesh is better, in some cases CF Mesh is better. And then if you want to go for Snappy Hex Mesh, there is a very good reference which is called Comprehensive Tour of Snappy Hex Mesh, a PDF that you can just Google, which was created by the original authors of Snappy Hex Mesh. And the official documentation on openfoam.com is now really good on Snappy Hex Mesh. I was really impressed by it when I saw it first. So you can just go to those two sources and then learn more if you're not satisfied with your mesh quality.
That's super cool input, Jozsef. Thanks a lot. Now moving to the processing part. Of course, we covered boundary conditions and numerical settings. Also, what I see, for example, when people ask in the forum or contact me, they always have this problem with this yplus. It's physically might make sense, but can you maybe in your own terms explain what is yplus and how can you approach it the best?
Well, it really depends on the turbulence model. So some turbulence model assume, so how I like to describe it in my courses is that for turbulence, you need high velocities. And because close to your wall, your velocity will be, or on your wall, the velocity is 0. So there has to be a sublayer where your velocity is so small that it becomes laminar. And this is the so-called viscous sublayer. And the question is whether you can describe this viscous sublayer with your mesh. And with the RAS, the Reynolds average models, you assume that you cannot describe this. So the assumption is that the distance between the wall and your first cell center is bigger than this viscous sublayer, and you solve it with some kind of empirical equation. That was found out decades ago, and then you just assume that it is correct. So this yplus value just gives you whether you depict this sublayer with your mesh or not. And if your mesh is too fine and your yplus value is very low, then you're good. Then you don't have to use the wall functions. The problem is if your mesh is too coarse, because then the assumptions are not correct regarding the height and then the wall functions, and then you have to decrease your mesh size. And sometimes due to calculation the power and your hardware, you cannot afford that, and then you just have to know that close to your walls you will always make some kind of errors.
Yeah, makes sense. I hope the audience, especially beginners in the field of CFD, understood somehow what this yplus now is.
I mean, you have a very good reference on wall functions, so they can check out your reference, and also there is a rather good description on Wikipedia. Usually you don't recommend Wikipedia, but the law of wall, if you Google law of wall and Wikipedia, then there is a nice picture and also a rather good description of this problem.
Yeah, thanks a lot for your input, Jozsef. Here, coming now to post-processing. Where should beginner look at when they look at the post-processing? Because a lot of people look at the convergence, and a lot of times it's like, okay, convergence goes down, I'm fine. So how do you see that?
So you mean in steady state simulations?
Yeah, for example.
Residuals are just a hint regarding convergence, and also the residuals are dependent on your mesh refinement. So it is always case dependent. What is your threshold value? Is it 10 to the power of minus 3, 4, 5, 6? I had projects where I had to go down until 10 to the power of minus 18 to have a convergent result. So convergence is not always the final value that you should take a look at. You should take a look at does the field change, the pressure. You can take the pressure drop. Does that remain constant, or the difference between inflow and outflow? So your fixed value on the inlet, is it the same value as what you get on the outlets? Or is your outlet value just constant? Or turbulent values, I really like to visualize nu T, because the nu the turbulent viscosity is oscillating if your simulation is not convergent. So just to visualize it in ParaView, does it remain constant? And sometimes your residuals are still around 10 to the power of minus 4 and 5, and you want to go down to 10 to the power of minus 6. But if you take a look at the results in ParaView, the results do not change anymore considerably. So residuals, yes, because you can visualize them during runtime. But now with the possibility of runtime post-processing in OpenFOAM, you can also visualize other quantities like inflow, outflow, pressure drop, or just pressure value at outlets. And then you can also visualize them during the runtime, and then open up the results and then take a look at key values, pressure, turbulent values. Do they change? Because maybe you are just doing overkill with your residuals.
How do you see force as a post-processing quantity?
If it is important, then this can also be a post-processing quantity, whether it remains constant or not.
Yes. Got it. So obviously we talked a little bit about your company, eulerian-solutions. If someone wants to delve into the field of entrepreneurship, what tips would you give them?
So currently it's June 2020 and we are still having the corona situation. So currently I would not advise to start your own company. So just keep your job and then wait for it to resolve itself, because it will go away. And then once you think you would like to start your own company, then it is important to make a name for yourself. And then there is this problem that without any projects, how can you make a name for yourself? And you have the possibility during your PhD thesis, or if you have a postdoc, then just make a name for yourself. And it is, how can you do that? It doesn't matter, just do it. Do something constructive in your field. So if you're talking in OpenFOAM, then in your field of OpenFOAM. But if you're doing structural mechanics simulations, then in your field of structural mechanics or wherever you work. So contribute, for example, an OpenFOAM code back to the community, or write publications, go to conferences, talk to people, or join events. I have on my YouTube channel the 2 such events: the online international meetings for users of OpenFOAM, which is a small kind of conference, or the community Christmas competition, which is a fun event where I ask people to solve fun problems with OpenFOAM, so that people recognize your name. I saw this guy at the event on YouTube. I saw also him at the conference. I saw publications of him. I saw that he contributed code, and then people will recognize your name. And then when you have your own company and you approach people, or people approach you, they already know you, or at least they have the feeling that they know you, and you have been validated already, and they can then hire you as a consultant. So it is really making a name for yourself, and prepare yourself that first it will not pay off. You will invest more time than what you get back, but this is just how it works.
I mean, we both as YouTubers, quote unquote, we know how much work it actually is, and the amount or the quantity you get back is sometimes a little bit less than you expect, but I think it's a long-term process, right? It's more of a marathon than a sprint.
Sure, and it's also just helping others. It's not just about getting something out of it, but also helping others. People helped me when I started, so I see this also as my duty as an experienced user to help others.
Yeah, that's so cool. I see it the same way, Jozsef. That's cool. Any closing words from your side? Where can people find you? I mean, of course, you have a big YouTube channel, which I'll link down in the description. Any other pages or websites where people can find you?
Yeah, so you can find me on YouTube, of course. Then you can find me on Patreon. If there is a link on my YouTube channel to Patreon if you want to support me, and if you like the content that I share on YouTube and Patreon. There is my homepage, eulerian-solutions.com. You can check that out. And yeah, otherwise look for me at conferences and user meetings. I like to join at least the Austrian user meetings or the workshop, and just reach out for me there.
That's awesome. Jozsef, thank you so much for this crisp and very interesting podcast from your side, and I would like to thank you so much, and hopefully there will be a second part, let's see, in the future, maybe about another topic. Let's see, but let's see what the future brings. Thank you so much, Jozsef.
Thank you for having me.